Welcome to our midterm demo video. Our project is TEX-RAY, textile identification via Raman spectroscopy. Our team members consist of Ariana, PSC, Danielle, PSC, Austin, CPE, and Cameron, EE. Our project TEX-RAY utilizes Raman spectroscopy to acquire the Raman fingerprint of a textile sample and sort the sample as being cotton or polyester. This will enable users to verify the fabric composition of their clothing items. It also enables a product comparison feature, in which users can store and keep track of the spectral signature of their authentic items. This allows for verification of authenticity of any replacements or second copies purchased of their database items.
This chart details all of our important engineering requirements. The highlighted rows are the demonstratable requirements that we will explore in this demonstration. The system should be able to identify a textile sample with 90% accuracy, the user should receive a readout result within 15 seconds of initiating analysis, and the system should also be able to compare the composition of different products with 90% accuracy.
Let's go through a brief overview of our subsystems, as shown in our hardware block diagram depicting the flow of our project design. We will first discuss the probe optics, then the spectrometer optics, then the electronics and software powering the whole system. Let's begin by looking at the laser that will enable the probe optics to collect the Raman signal. Okay, here we have the laser connected to the probe optics system, and it's currently being controlled, turning on and off every 2 seconds. Here's a circuit allowing it to do so. We have the ESP32 connected to a resistor at GPIO 18, which is connected to a transistor. And then we have the LED, the red LED indicating that the ESP32 is receiving the proper voltage, as well as the green LED indicating that the laser is receiving the proper voltage. Here we have a 12-volt DC input for the laser, as well as a 3.3-volt DC input for the ESP32. The way we have it set up right now is the code is cycling on and off every 2 seconds, pulling the resistor high to low and interrupting the ground connection for the laser, which is turning it on and off. The next step would be to connect it to the Raspberry Pi alongside the LCD display. And instead of it cycling on and off, it would then be turning on and off via input on the LCD display. Here's the same circuit with the addition of the Raspberry Pi and LCD connected to the breadboard. I initially pressed it off. Now I'm turning it on with the press of the button, showing we have proper communication.
This is a temporary setup for the probe optics as we were testing Raman signal acquisition. After the laser is turned on via user input on the LCD, it is passed through a bandpass filter and then a beam expander setup to clean and enlarge the beam. This beam then hits the 45-degree dichroic mirror and is reflected onto an 18mm focusing lens to create a tight focus on the sample. Any Raman scattering that occurs is recollimated by the focusing lens, passed through the dichroic mirror, then isolated by a long-pass filter. A 75mm focal length lens couples the signal into an optical fiber for the blue wave miniature spectrometer. In the final system, our custom-built spectrometer will take the place of this fiber. Using this test setup, we collected data from an ISO-adjacent cotton sample 3 times and recorded the spectrum each time. The integration time used for each trial was 10 seconds, keeping in mind that our engineering specification stated we should have an overall system response time of 15 seconds. For each trial, we placed the sample, let the 10-second integration time run, collected the spectrum, then removed the sample. We allowed the spectrometer to zero out before placing the sample back and beginning the next trial. As expected, all 3 trials resulted in spectrums that were comparable to each other, as the Raman fingerprint of the cotton sample should be mostly consistent from trial to trial. The only inconsistencies should be due to noise and fluorescence, which will need to be filtered out on the software side later on. On the right is the documented Raman spectrum of cotton fabric based on existing literature, and on the left is the result of our 10 trials. Key peaks around 567 and 575 nanometers, corresponding to 1100 wave numbers and 1380 wave numbers respectively, are clearly visible in our results and are relatively consistent between trials. It is important to note that our graph shows the results of our raw data with only the noise floor subtracted. There is still a lot of fluorescence and background noise present, and flattening algorithms need to be applied to our data to clean it up and make it appear more like the spectrum on the right. Among this, improvements to the SNR need to be made through additional testing, though our current data is still visibly consistent in its overall shape, which is a good sign. We took 10 trials of an ISO-adjacent polyester sample in the same manner as the cotton sample previously shown, and the results of those trials are shown on the left. The right displays the Raman spectrum of polyester as found in various literature. The most important peaks for the identification of polyester are at 1600 wave numbers and 1730 wave numbers, corresponding to approximately 583 and 587 nanometers respectively. These peaks are consistently present in all of our trials with the high intensity despite the background fluorescence. The polyester trials were slightly more consistent and had somewhat more prominent peaks than the cotton trials shown previously. To test the product comparison feature, we did 10 trials each with a pencil case, a Chemtech wipe, and an umbrella to determine if the spectra of miscellaneous samples would remain consistent and distinct. Though we don't know the exact composition of these items, and thus can't anticipate any particular peaks of interest, each trial should generate the same shape spectra based on the principles of Raman scattering. The results remain very consistent within the 10 trials for each item. Though the spectra of the pencil case and the Chemtech wipes appear similar in shape, there are clear differences within the dips and peaks of each spectra that separate them, and these differences are clearly reproducible. The umbrella spectra were very different in shape from those of the pencil case and wipes. However, once again, you can clearly see the same peaks and curves being replicated across all trials. The result of this testing means that the product comparison feature should function well in our final product. Exact analysis of the accuracy of both our material analysis and product comparison tests will be discussed later on in the software section.
The spectrometer portion of TEX-RAY is responsible for separating the Raman signal from the probe optics into its constituent wavelength components. This is a prototype for the reflective spectrometer configuration used in our system. For the prototype, we're using a 50mm plano-convex lens to couple light into the spectrometer. This is okay for testing purposes, however, I must note that in the integrated setup, a 75mm achromatic lens will focus the Raman signal onto the entrance slit of the spectrometer. The 25 micrometer vertical slit acts as a spatial filter and is the primary resolving element of the system. The light will diverge through the slit and be collimated by a 50mm achromatic lens. This collimated beam will then be incident onto a reflective diffraction grating with a groove density of 1200 grooves per millimeter. The diffraction grating will disperse the Raman signal, bending different wavelengths at distinct angles. This angular separation enables resolution of the individual wavelengths that correspond to the various vibrational modes of molecules within the fabric. The light dispersed from the grating is focused onto the linear ray CCD sensor by another 50mm achromatic lens, which will form an image of the entrance slit onto the detector plane. This means that different wavelengths will appear at different positions along the linear ray CCD, allowing us to detect the Raman spectrum from the sample. To evaluate the spectrometer's performance, we will use a fluorescent light source to assess the receivable spectral range and the system's resolvability. Fluorescent light bulbs are ideal for calibration due to their strong mercury and phosphor emission bands in the visible wavelength range. Specifically, emission bands from approximately 540 to 630 nanometers closely align with the expected detectable range of our system. Notably, some peaks are spaced by approximately 3 nanometers. We could further estimate the system's spectral resolution with this reference. I began by establishing an optical axis with a green laser and placed the prototype along this axis. This ensures that we'd be able to maximize the throughput of our signal. I proceeded to couple the light from the fluorescent bulb into the system. The resultant images of the fluorescent spectrum were taken with a Thorlab CMOS camera. As a disclaimer, the resolution and spectral range of a spectrometer system are heavily determined by the detector used. While we do expect different results when our system is interfaced with the CCD, this testing offered a sanity check. Using MATLAB, images from the CMOS sensor were processed and calibrated by manually matching the most intense peaks from a fluorescent reference spectrum to the image. A polynomial fit was used to convert pixel position to wavelength, followed by smoothing and normalization to produce clean, well-defined peaks. This experimental spectrum ultimately aligned with the reference spectral lines. To assess the resolution, I took the average full width at half maximum of the peaks across the two images. This resulted in a 0.46 nanometer full width at half max, which is within our spectrometer's resolution requirement. We know our spectral range requirement is met. This process establishes our calibration approach for integrating the spectrometer with the CCD in its final housing. The next steps include refining the spectrometer's alignment, integrating with the CCD, and coupling with the probe optics.
Here we're showing the CCD and STM boards. You can see the hex inverter and capacitors and resistors all used to clear the input and output signals of both devices. Here we have the CCD with each non-STM port connected to ground. And you can see the output signal of the CCD through the oscilloscope. The peaks every 7.5 milliseconds is the start and end of each frame. And the fluctuation there you can see is me moving my hand across the CCD from start to end, which you can see in its respective location in each frame. Here we have the STM code written in the STM Cube IDE. Here we have the 6 peripherals used. Those are the 4 timers used to drive the CCD, 3 of which control the input to the CCD. The remaining is for the ADC, which you can see here. The DMA is used to transfer the data, and then the ADC peripheral is above it. There you have the buffer used to store the output before sending it on the USB. Here we have the initialization of all peripherals used, as well as the start of the 4 timers and the delay used before the shift gate is begun. Here we have the while loop, which is the command that begins to send the data. And if we scroll down here, you can see what is being called within the while loop. This transmits the data using the VCP connection over the USB cord. So again, that's here in the while loop, which will send all the data. Here we have Cool Terminal, which is what's being used to show the raw binary data being sent over the USB using a VCP connection. The connection is being established right now, but isn't shown on the screen recorder, which only shows the window. But when we press connect, you can see the raw binary data being shown. This is when it's normal. When my hand is removed, it goes to here, which shows the lighting change. The flashlight is then added to above the CCD as I put my finger at the center, which we'll see in a second once the data is transferred. Here we're stopping the recording of the data. So once I'll convert it next in the Python code, you'll be able to see my finger show up over the center of the CCD once this raw binary data is converted into integers and a text file, which will then be shown on Excel in the form of a graph, which you'll be able to see each frame. So we disconnect here and close the terminal. Here we have the Python code that's responsible for converting the file of raw binary data taken from CoolTerm and turning it into a text file in which each pixel of binary data is converted into an integer, as we can see there with the converted data type. You can't see, but the file is being selected. It's then seen in the corner there, downloaded. We put it into a Google Sheets file. It's added and downloaded, and it'll take too long to convert to show here, so we'll move on to the next video where it's shown. Here we can see the loaded in file where you have each of the integer pixels loaded into this column. We can see the first 6,000 here loaded into this graph where you can see my finger placed along the center of the frame. Here we have the Python code where the comparison algorithm is run. In this file, it'll be run against Python and polyester data. First, taking the external dynamic time warping library that's used for the comparison, which everything here is done in the Google Colab environment. First, we upload the data trials of all 20 for 10 polyester and 10 cotton trials, which we can see here. This is all loaded into the code here. This is the dynamic time warping function call, which you can see here, which will return each similarity score. Here we have the labels for each trial applied, so you can see at the end which similarity score belongs to which. Here is the beginning of the noise filtering, in which a Savitsky-Golay filter is applied for each to create a baseline of noise and fluorescence, which is then subtracted from the data at each trial, which you can see here. And then this is the second dynamic time warping function call, which is used because the dimensions of the data has now changed, which you can show there. Here we have the smooth dynamic time warping function call, and the results are then applied for labels like before, and the end results are shown here printed before and after noise reduction. This will be done in the final project with k-nearest neighbors, but for now we're using the actual manual results in order to know which trials are closest, rather than just a listing of which sample is being identified. We actually have each trial to know going forward what needs to be done in order to better improve the system. But here you can see the closest trials are all cotton, so this will be sorted into cotton in the finalized system, and as we have it right now. Here we have the results of the first sorting model. Each trial was run 4 times with a different number of nearest neighbors considered. In total, the first model showed an accuracy of just over 81% across 80 trials, which is acceptable for the first model, given the area of improvement still available for us in the project. Here we have the second Python file in which the comparison algorithm is used. Instead of cotton and polyester data, we have object data of an umbrella, cam wipe, and pencil case. The first thing done again is importing the external dynamic time warping library. Here we have the 3 datasets mentioned previously, as well as the noise data, which is the laser running for 10 seconds without a sample being used, which will be subtracted from the datasets previously mentioned as a form of noise reduction. Here we load in the data files, which are SSM files again from MATLAB. The background is subtracted, as I mentioned just before. Then the dynamic time warping function call is done using the test data against all previous trials. Labels are added for each dynamic time warping result to know where it is being compared against. This is printed raw compared to later where we have noise reduction done by the Savitsky-Golay filter, again adding a noise baseline through smoothing filtering, and that'll be subtracted much like the noise dataset previously shown from each trial. Here we have the second dynamic time warping call, which is used because the dimension of the data changes after the Savitsky-Golay filter. And again, this is printed with the label being shown again. And here we can show that the umbrella case was matched with the 9 previous data sets, which means that it's guaranteed to be matched. And again, we can see that it was matched after the Savitsky-Golay filter, although since the differentiation between the 3 samples is much easier than cotton and polyester, in this case the filter is not needed because the results are very much the same in terms of classification among the 3 samples. Here we have the results of the model with product analysis using the umbrella, Kim-Wipe, and pencil case data shown previously. In 30 trials, the accuracy was around 77%, but this is expected to improve considerably and soon with further noise reduction and better product sampling.
After analyzing all of our subsystems separately, this is where we stand in regards to our engineering requirements. Our material analysis accuracy and product comparison accuracy are slightly below the target, but we are still improving our optical alignment and algorithm to increase these values. Our total response time was estimated by considering our spectrometer integration time and software runtime, and came out to be approximately 15 seconds, which is on target.
Thank you to Chroma for generously lending us a dichroic mirror and long pass filter, and to Test Fabrics Inc. for providing us with industry standard fabric samples. This has been our project, TEX-RAY.